So earlier we were talking about changes in energy. We can measure the change in energy for a chemical reaction using these concepts that we've just talked about of the heat and the work. Heat is mc delta T, work is negative P delta V. And so we can look at an exchange of energy between the system and its surroundings. And we have two different ways of quantifying some of that energy change. So we can do what's called constant volume calorimetry and measure the change in internal energy. The change in internal energy is going to be equal to the heat plus the work. Now, if there's no change in volume, because what we're talking about here is that pressure volume work, so work is negative P delta V. If delta V is 0, then the work is 0. That make sense? So when the volume is held constant, then the work is 0, and that makes things simpler, and we can just say that the change in internal energy for the reaction is equal to Q, the heat transfer. We put a little V there to say this is happening at constant volume. It isn't practical to measure the temperatures of individual reactants or products in a reaction, because how do you take the temperature of sodium ions, right? It just really can't be done. So just like with the block of metal in the beaker of water, what we do is we use a controlled surroundings where we can measure the change in temperature conveniently, and we know that the heat absorbed by that controlled surrounding is going to be equal to the heat lost by the reaction that's occurring. And one way of controlling those surroundings is using what's called a bomb calorimeter. So Q for the system, this would be the reaction we're interested in, equals negative Q for the surroundings. We're going to make the surroundings this bomb calorimeter. So that's the same as negative Q cal. The change in heat, the change in energy for the calorimeter. Calorimetry is what we call this. It's a technique used to measure heat of reaction by observing changes in temperature. So we've got our system. We're defining that as the chemical reaction we're interested in. And we have the surroundings. We're going to make this the bomb calorimeter. And there's heat being transferred between these. And we can observe the change in temperature of the surroundings. So this is an illustration of a bomb calorimeter. This is the bomb inside. It doesn't explode. So in here, this is often used for measuring calorie content of foods, and that's done by burning them and seeing how much energy is released. So you can put your sample in here. There's oxygen in here, and there are ignition wires, and this is tightly sealed. So it's not that the bomb's exploding, but there's actually sort of an explosion going on inside the bomb, but the bomb holds it all in. It's airtight, won't let any of the stuff out, and so the volume of this chamber is constant. When this sample burns, it's going to release energy. It's going to release heat. That heat will be absorbed by the water inside the outer compartment of the calorimeter. We've got a stirring mechanism here so that we can make sure that the temperature of the water is uniform throughout. We take the heat being given off here and distribute it around, and we have a thermometer and we can measure the temperature. This part is highly insulated, and so we can be fairly confident that none of the heat is escaping onto the bench top or the air or anything like that. So Q for the reaction will be equal to negative Q for the calorimeter, or we can say Q for the calorimeter is negative Q for the reaction. Q for the calorimeter we've been talking about MC delta T. We've been doing Q equals MC sub S delta T. The specific heat capacity for this calorimeter, because it's always the same, instead of using the mass and specific heat capacity all the time, these two terms combined are the heat capacity, not specific heat capacity, the heat capacity of the calorimeter. That's specific to this particular calorimeter, but it's always going to be the same. So Q for the calorimeter is its heat capacity times the change in temperature. And that allows us to calculate Q for the reaction. Q for the reaction is equal to Q at constant volume, which is the change in heat for the reaction. So let's work an example. When 1.55 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, determined in a separate experiment, is 5.73 kilojoules per degree Celsius. So let's pull out these numbers. I've got 1.550 grams of hexane, and that's a mass. We have the temperature changing. The initial temperature is 25.87 degrees Celsius. The final temperature is 38.13 degrees Celsius. So we could calculate the change in temperature. That's the final minus the initial. So 38.13 minus 25.87, 12.26. We're told the heat capacity for the calorimeter is this number here. That's C for the calorimeter, 5.73 kilojoules per degree Celsius. So for this constant volume calorimetry, Q for the reaction is equal to negative Q for the calorimeter. The heat lost by the reaction is gained by the calorimeter, or if it's an endothermic reaction, the heat gained by the calorimeter is lost by the, the heat gained by the reaction is lost by the calorimeter. Qcal is C for the calorimeter times the change in temperature. This C includes specific heat capacity and mass. And we'll be using that in our experiment today as well. Well, we have the heat capacity for the calorimeter and we have the change in temperature. So we can plug those into this equation. Q for the reaction equals negative times 5.73 joules per degree Celsius times 12.26 degrees Celsius. Sorry, that's not joules, it's kilojoules. So the degrees Celsius cancel out. We can calculate this. So I've got negative 5.73 times 12.26. Q reaction is negative 70.2498 kilojoules. Any questions yet? Is that the answer that's requested? No. They want to know kilojoules per mole of hexane. Was this 1 mole of hexane that we burned? No. But we're given a mass, and we've got the formula, so we can figure out how many moles. So the molar mass for hexane is going to be 6 times 12.01 plus 14 times 1.008. $86.172 grams of hexane per mole of hexane. So delta H for this reaction, it gave off 70.2498 kilojoules for how many moles of hexane? Well, we need to convert that mass to moles. 1.550 grams times, moles on top and grams on the bottom. 86.172 grams is 1 mole for hexane. .017. Our mass had 4 significant figures: 179872 moles. So I take the amount of energy released by this specific amount, divide by the number of moles, and then I get units of kilojoules per mole. So this is negative 3905.52, and it just keeps going. Sig figs. This one has 3, this one has 4. This is going to be 3 significant figures. What should I round that to? 391? No, because this is 3,000, right? 3,905 rounded to the nearest 10 is 3,910. So I can say minus 3910 kilojoules per mole. Some of you would be much better off putting that into scientific notation. In scientific notation, you don't have to worry so much. Minus 3.91. So this is the digit I'm keeping. The 5 makes me round the 0 up to a 1. Times 10 to the, I'm moving the decimal point 1, 2, 3 places. It's a large number, so the exponent is positive. Delta H for this reaction is negative because when hexane burns, it releases energy. It loses energy. Any questions?